Hi everyone, welcome back to PrepFusion. I'm Anish and today we'll be starting the lecture 5 of polar plots, right? So in previous lecture we learned about few relative stability parameters, right? Like the gain crossover frequency and the phase crossover frequency. So what does gain crossover frequency means? Gain crossover frequency means where my magnitude of my OLTF, the frequency at which my magnitude of OLTF becomes 1. And what is my phase crossover frequency? The frequency at which my angle of my OLTF, right is minus 180 degrees. We understood like why we are interested in that minus 1 and minus 180 degrees, right? Sorry, one magnitude and minus 180 degrees, because obviously due to finding the stability we understood that at that point, that critical point, right, I have a crossover frequency. Basically either it will go from right hand plane to left hand side of the S plane, or from the right hand side from the left hand side to the right hand side of the S plane, right? So these two things can happen, right? So like now what can I say, like how to find the stability from that we'll understand, but let us first study few more parameters like the gain margin and the phase margin. What is gain margin and phase margin for a closed loop system, right? So let's first read the definition and from there we'll understand it better. So gain margin, right, it is denoted like kg, or you can say it like this one, kg or gm itself. Kg or gm. Okay, so it is kg or gm. So it is basically the reciprocal of magnitude of g of j omega into h of j omega at phase crossover frequency. Now we know what phase crossover frequency. Basically phase crossover frequency is the frequency at which my angle is minus 180 degrees, right? So if like gain margin is the reciprocal of the magnitude at that point, right? Magnitude at that point. Why? We'll understand. Basically this is defined as like this one, and kg in dBs, right? Now in normal absolute units, absolute values, this is defined like this one, and in dBs it is defined like this one. We just simply take the log of this one, and log of a reciprocal number, right? If it comes in the numerator it becomes negative sign. Basically this is to the whole to the power minus 1, so this minus 1 power comes in front of the log sign, right? So basic log properties I hope you understand. So this, right, I'm just showing you in rough. This I can write it as, I can just copy this one. This is to the power minus 1, right? Simply I can write minus 1. Now if I take the log of this one and multiply 20, what will happen? This power, right, power comes in front of the log. So minus 1 can come in front of the log. Simple log property, right? That's why I get minus 20 log this whatever this magnitude at what is the at phase crossover frequency. Sorry, this is actually at phase crossover frequency, not at g. Sorry, my mistake. So here, right, people generally tend to make mistake. So you have to be very careful that what do you have to be careful about? So basically my gain margin, right, it is a function of phase crossover frequency and not gain crossover frequency. So there is generally what happens is bit of confusion, right? Students tend to get confused. So my gain margin I should write here. Let me write here itself. This one a bit behind actually. Yeah, sorry. Let me check if my camera is fine. Yeah, it is fine. Yeah. So my gain margin, right? Gain margin is a function of omega p and not a function of omega g. Okay, not a function of omega g. So gain margin is a function of omega p and not a function of omega g. Okay, so all these things we got to understand, right? Now like, yeah, don't get confused with this one. Next parameter will be a bit different. So like what does the physical significance of gain margin mean? So obviously graphically I will show you this one, right? Graphically I will show you, but for now just try to like listen to what I'm saying, right? So the physical significance of gain margin is basically, it is the additional amount of margin left for it to become like marginally stable. Okay, if you don't understand, don't worry, obviously I will show you graphically, there you will understand. Additional amount of margin left for it to become unstable, or you can say marginally stable, because at that critical point, right, the system goes to marginally stable. Okay, or unstable I say, because after that at that frequency it will anyways be unstable, right? Okay, so yeah, this is what this one is, and this is the like a value of gain margin. Graphically I will like will see how am I telling this, right? Graphically see. Now what is the next parameter? Next parameter is the phase margin. So phase margin is denoted like this gamma, or you can say like this one, PM itself, right? Okay, PM itself. So what does my phase margin mean? Phase margin means the additional amount of phase lag that needs to be added to the phase of the system. The additional amount of phase lag I need to add to the phase of the system at omega equals to gain crossover frequency. So at gain crossover frequency, what happens? My gain is 1. Okay, but my phase is something else. Phase is something else, right? To bring the system to on the verge of instability. Because if I add it 180 degrees, what will happen? My gain is 1, and if my phase also becomes 180 degrees minus 180 degrees, then what will happen? It will become marginally stable. Basically I will have a crossover frequency at that point, right? That's why this is known as phase margin. And here, right, my phase is minus what I know, but if I make the gain of the system also 1, like a magnitude of the system also 1 at that point, right, then what will happen? My system will again become unstable, right? My system will again become unstable. So yeah, this is basically it for this one. Now, like again, right, okay, yeah, I did this, right, and again you should be very careful that your phase margin, right, not with some different color, your phase margin should be basically a function of omega g and not omega p. Okay, not phase crossover frequency. Okay, so this one is this one. Now basically what does this mean? Like, why is 180 getting added? But phase margin is what? The additional amount of angle that I need to add to get it to minus 180, right? So currently what is my angle? Let's say like my angle is this, right? Currently at gain crossover frequency my angle is this, but I need to add some angle to make it to 180. Okay, let's say my angle is minus 150, right? Minus 150. Now how much amount of angle that I need to add to make it to minus 180? Basically if I subtract with this minus 180, right, then I will get the amount of angle that I need to add to get this point, right, get this angle to minus 180 degrees. So what is the angle? It is basically 30. So here, right, if I see like from here also you can see like with 150 how much I need to add. Minus 30 I need to add, right? Minus 30 I need to add. But like as phase margin is a positive number, so that's why we tell like this one basically. So yeah, like phase margin is how much additional amount that I need to add to the phase lag. Basically phase lag it is. So this is phase lag, right, not lead. So whatever happens in the lag is in the negative direction, right, in the clockwise direction. So you can say in the clockwise direction how much I need to add. Okay, in the clockwise direction. So just be careful about that. Sometimes you may get confused that I'm adding in the clockwise direction, but still like you might say that with 150 I just simply add 30 degrees, it won't work, right, because it will go to minus 120. No, I am adding 30 in the clockwise direction. So just be careful about that. Phase lag means adding 30 in the clockwise direction, right? Sorry, phase lag means clockwise direction, so that's why it is positive and it is fine. So I'm adding 30 in the clockwise direction, that means I'm adding minus 30. Okay, just be careful about that. Arey yaar, what is happening with this one? Okay, just hold on a second, something is wrong with my light. Okay, there is a maximum. Okay, yeah, sorry actually. So yeah, we are adding in the clockwise direction basically. That's why I can say this comes up 30, right? So we are in the clockwise direction. So this, right, this minus and minus, like this is a repetitive process, right? So this 180 minus 180 is fixed. So this minus minus becomes plus. So here I get plus 180, right? Plus 180. Okay, that's how this formula comes up, right? That's how this formula comes up of 180 plus g of j omega, right? 180 plus g of j omega. Okay, so yeah, that is basically it for the phase margin. And just be careful that my phase margin is a function of phase crossover frequency. Okay, so like let's I will like tell you graphically, but first let's read few points, right? The OLTF does not have any, like if the OLTF does not have any poles slash zeros in the right half plane, both the gain margin in dBs and the phase margin in degrees, right, should be positive to ensure the stability of the closed loop system. Like this is one condition we'll understand. Like even if my, let's say, gain margin is negative, then also my system can be negative, then also system can be stable, right? Then also system can be stable. Okay, we'll understand this stability condition later stage. Just we are getting started off with the relative stability parameters and how to find them. Obviously, how to find the stability with the help of relative stability parameters, we'll understand that at a later stage in the next few lectures, right? For now, like this is for true if both my phase margin and gain margin are positive, right? Positive, like gain margin in dBs is positive and phase margin is in degrees is positive, then for sure, for 100% sure, my closed loop system will be stable. Okay, my closed system will be stable. Okay, but even though sometimes if my gain margin is less than 0 and phase margin is greater than 0, then also my system can be stable. When will that happen? We'll understand. Okay, so I'm not talking about stability right now, I will talk about that later. But here, right, why is this the case? Why is this the case that my system will always be stable? Because it is never cutting the -1 point, right? It is never cutting the critical point, right? Never cutting the critical point. That's why system will always be stable. System will always be stable. Okay, that is for sure. So cutting the critical point of -1, 0, right? We don't have a crossover frequency, hence it is always stable, right? So this is for sure, but for other conditions we'll see, right? I'm just not talking about it right now. We'll talk about it in the next few lectures. For now, I'm interested in how to find the phase margin, how to find the gain margin, and what are the significance of those two, right? Okay, graphically. So yeah, let's understand one thing, that let me take one example. Here I have, I think, one example. Yeah, here I have one example, right? Here I have one example, that if like my transfer function is like this one, we already plotted the polar plot for this one, right? Already plotted the polar plot for this one. So this one is the polar plot for this, right? And let's say like the point at which it is here, right? It is something less than -1. Okay, -1 is here and it is something less. We're assuming that it is something less than -1. So what is happening? What am I doing with gain margin, right? So how to make this one unstable? How to make this one, or you can say, marginally stable? So if I somehow, this is -180 degrees, right? If I somehow at this point make this to -1, right? Magnitude also is 1, right? Then what will happen? Then basically my angle condition and my magnitude condition both will satisfy for the same frequency. And if that is satisfied, then definitely that particular frequency will be the crossover frequency, and definitely my system will become unstable. Okay, will become unstable. Basically, will become marginally stable. So it will either go from right hand side to the left hand side of the S plane, or from the left hand side to the right hand side of the S plane. So let's say I multiply it with some gain k. So currently it has some gain, whatever gain it has, right? Whatever gain it has. Now I multiply it with some x, right? So currently the gain is k. Okay, let's say the currently gain is k, and I'm assuming that my k, right, k is less than 1. Okay, so magnitude of k is less than 1. That is what magnitude of k is less than 1. Okay, so magnitude of k is less than 1. So if I multiply k times x, right, what do I get? If I multiply k times x, like I'm multiplying both the gains. So x is the amount of multiplication that I need to do for it to reach to this point. Okay, so I should not do this like the distance. What I should do is like make this arrow, right. So what is x doing? X is getting multiplied with this point and transferring it to -1, or you can say the magnitude becomes 1. Phase is 180 itself, so it is negative itself. No worries, negative real axis, it is on the negative real axis. But if I multiply with k into x, right, I get 1. Magnitude is 1. Okay, then what is happening? Basically, what is my x equals to? X equals to 1 by k. Okay, what is this? Like, what is k? K, right? Let me write here. What is k? So k is the magnitude of j omega into h of j omega, basically the OLTF at omega equals to omega equals to omega g, omega p, basically at phase crossover frequency, right? Omega p, right? So when my angle is -180 degree, so this is what my k is, right? So now if I replace my k, right, g of j omega p into h of j omega p. So this is my k, right? This is my x. What is x? X is the basically the gain margin, the amount of gain that I need to multiply to get it to -1 point. So that is what here, right, I've told, right, reciprocal of that, the additional amount of margin left for it to become unstable. Basically, it is the amount of margin, if I multiply, it will become unstable, right? So that is the amount of extra margin that is left. So even though my like frequency response may vary, right, vary slightly, still I am not cutting this point. Okay, so up until I'm not cutting this point, my system still will be stable, right? System still will be stable. How is this stable? Like my that will understand, right? That will understand graphically. But for now, like you are understanding, right? No crossover points. That's why system is stable. My system is always on the, like the poles are always on the left hand side of my spline. For now, if it touches the -1 critical point, then obviously there is a crossover frequency. There will be a right hand, like there will be poles on the right hand side of my spline, right? So yeah, that is one thing. That is one thing, right? Okay, sorry, I had to like pick up a call basically. So now what I will find is I will talk about the phase margin. We just learned about the gain margin, right? So let's say at this point, right? Let's say at this point my gain is 1. Okay, let's say my gain is 1 at this point. Okay, now what about my phase margin? Now what about my angle, right? What is the angle at this point? Okay, that I am interested in. Okay, that is what phase margin is basically. So the angle, right, angle is something like this, theta, right? Now you might ask, sir, why are you calculating the angle in clockwise direction? You can also calculate in anti-clockwise. Why? Because in most cases, right, if my number of, like most cases for realizable systems, number of pole is greater than number of zeros, most cases I will rotate in the clockwise direction itself. Sometimes you will not understand this what I'm telling right now. Sometimes what will happen, the zero comes before the pole, comes before the pole, then we will start off with anti-clockwise direction, then again we'll go to clockwise, because at the end, right, at the end what is happening, the number of poles will be always greater than the number of zeros, because for proper transfer function and for realizable systems, for real world systems, the number of poles will always be greater than number of zeros. Okay, so yeah, for that case, right, for that case, like I will go in the clockwise direction. That's why I'm calculating angle here in the clockwise direction. That is the reason behind this. Okay, that's why there always is some confusion. Why are you measuring clockwise? Why aren't you measuring anti-clockwise? Why is the phase margin here, right? It is written as phase lag, right? Okay, phase lag means clockwise direction. We have studied this in our phases chapter, right? Phases chapter. So yeah, I hope you got the point, like why are we interested in the clockwise direction basically. So basically, right, that is one thing. Okay, so this is the theta. Now what is happening, I want to shift this point to this -180 degrees. I want to shift this point to this -180 degrees, because this is the one, right? I want to shift this point to here to get the condition for instability, right? That is what this is telling. We want to bring the system to verge of instability. Basically, this is how much amount of more phase lag how much amount of more phase lag I need to add. Let's say this theta, right, is 150. How much amount of more phase lag I need to add? Another 30 degrees of phase lag I need to add to make it to like take it to the negative real axis, okay, of -1. Okay, that is the important point to note here. So this is theta. So how much more phase lag I need to add to get it to negative real axis? So I will write here negative real axis, right? So that is the basic thing. And what is this x? The amount again I multiply to, or I can say take it to -1 comma 0 point, or like not minus, but I can say -1 comma 0 point. Okay, so this is basically what phase margin is and gain margin is in graphical manner. I have shown you in graphical manner. Okay, so like what I can say about gamma, okay, or PM, right? What I can say about PM, okay, this is the GM basically. This is the GM basically. And what about the PM? PM is simply that again, right, -180, like angle of G of J omega into H of J omega minus of -180. So it becomes plus of 180. This is the phase lag. Just remember, this is the phase lag, not the phase lead. So this is not going, this theta, right, is not clockwise. This is, sorry, it's not anti-clockwise. This is clockwise, right? Why this is G? Because the gain at that point, right, gain of the voltage is 1. Okay, so this is in the clockwise direction. Just be careful about that one. Okay, in the clockwise direction. Okay, so I hope you get the point. Like, or how can you write this one? Like how am I getting this formula basically? So this is about the gain margin, right? What about the phase margin? What are the phase margin? Phase margin, like how much amount I need to add. So let's say gamma is the amount I need to add to this angle, right? Okay, gamma is the amount, like I wrote it directly here. I should write it like what do you understand by phase margin? So basically, right, I can say that I am adding some phase lag with it, right? Some phase lag. So how do I add phase lag? Basically, right, we subtract the angle, right? So if you are going the clockwise direction, we subtract the angle, and if you are going the anti-clockwise direction, we add the angle. Add the angle, right? So basically, what is my current angle? My current angle is G of J omega G into H of J omega G, and I have to subtract phase margin because I'm going in the clockwise direction, not in the anti-clockwise direction. That is very important, right? I'm going in the clockwise direction. So what I'll do, I will simply subtract my phase margin, the amount that I need to add a phase lag of to reach to what point? 180 degrees, right? 180 degrees. So this is this one. And now what is my phase margin basically equals to? My phase margin is basically equals to 180 plus g of j omega g into h of j omega g. Yeah, sorry for writing it again. I had to prove it to you, right? How does this formula come up, right? That is very important. But what is the important thing to note here? This phase margin is in the clockwise direction because I am adding some phase lag. That's why this negative sign is coming, right? That's why this negative sign is coming. So this negative sign is very important to understand. Why does this negative sign come up, right? Very important to understand. Okay, these are proof. Okay, not that important, but still you get the basic idea and overview of why are these terms coming. Okay, so as I also mentioned, one thing is like if my OLTF does not have any right hand poles or zeros, right? Both the gain margin, if both the gain margin and phase margin are positive, then the system will be stable. Why is this the case? Because, right, what do we know? What do you know? That how is my system stable? Like my system is stable. Like if it doesn't cross this crossover point, right? Then what does this mean? If it doesn't cross the crossover point, that means all my poles are on the left hand side of S plane. And what is my output defined as? My output is defined something like this. We already derived this one. If we remember this one, it was something uh, if I remember it correctly, a naught sine omega naught t plus phi. Okay, I can name this as b naught basically because a naught was the input amplitude, b naught sine omega naught t plus phi, right? Now plus I had few transient terms, right? Few transient terms. What are those? Like those were something like this summation going like this was CLM e raised to, and I had t times something m multiplied with e raised to power pmt, where pm were the poles, right? And like this was going from, like m was going from this 0 to some value n, right? And this there was like this L was going from 1 to some value k. Okay, I'm not very interested in the like all these things. I'm just interested in the form. I'm interested in pm. Like if this condition is satisfied, right, then my pm will always be less than 0, hence it will decay, hence my response will be stable. Response will be oscillatory, but it will not be unstable, right? Obviously due to input is oscillatory itself, so output will also be oscillatory. But due to this, right, if pm was greater than 0, then what would have happened? My system would have become unstable, right? That is more important. System, that's why I'm telling, as my roots, all of them, right, lying on the left hand side of my S plane, then like pm is negative, right? And if pm is negative, then like system will be stable itself. System will be stable itself, right? If let's say if my pm is greater than 0, what is happening? If my pm is greater than 0, what is happening? If my pm is greater than 0, then like it will not die down, right? It will regenerate. It will regenerate or get more energized, right? Regenerate. It will increase, or you can say now if it increases, then what happens? If it increases basically, right, so system will become unstable because response is not bounded, response unbounded, right? Response system unstable, right? System unstable. So yeah, that is what this thing point that it told, right? I forgot to mention it at that point of time, sorry. Like okay, so yeah, now like let's I told you what is phase margin and gain margin visual, right? So I should write this heading here. Let me reduce the size of this one. Understanding GM graphically. Okay, so yeah, this is basically it. Now, like I told you, now how to more accurately graphically locate my system, like in this like graphically. I told you, right, what is the procedure? Let me summarize it for you. The point where my polar plot is cutting the negative real axis, okay, that point is known as the what gain crossover, phase crossover frequency, because at that point my phase is minus 180 degree. But if let's say it is not equals, like at that point my gain is obviously not equals to 1, right? It is something else, so basically, what is the magnitude? Sorry, the magnitude of OLTF at that point is not equals to 1. It is something else. So I need to multiply with it some value to get it to 1 itself, so that I can get to my critical point. So that is how we understand, like that is how we found out the gain margin, right? How we found out the gain margin. And for phase margin, what you can do is, like, you can simply draw a circle, right, of unit radius. If you draw a circle of unit radius, what you will see, the point at which the circle and the polar plot are intersecting, that point is basically known as the point of like gain crossover frequency, right? Gain crossover frequency. So at that point my magnitude of my OLTF is 1. Okay, phase is obviously not like minus 180. I need to transfer it to minus 180 so that I can reach my critical point, right? If I reach my critical point, then again my system will become stable. Up until this point my system is system will become unstable, and up until this point my system is stable, right? Okay, so let me write it down, right? Let me write it down. So let me write down the procedure, right? So I will just pause the video, and like again I will after writing it down I will again restart the video, right? Thank you. Okay, I have written it down actually, all the points basically. So how can I graphically locate my omega g and omega p basically? So let me quickly again give you the recap, right, what I told like just a few minutes ago. That for omega p, right, for omega p, the point at which my polar plot is cutting the negative real axis, at this point, right, it is cutting my negative real axis, that point will be basically the omega p. Okay, the frequency at that point will be omega p, phase crossover frequency, the frequency at which my phase is minus 180 degrees, it is crossing the negative real axis. And what about the omega g, right, the point at which my polar plot is cutting the circle of unit radius whose center is at origin. Okay, so if I draw a circle of unit radius, right, the distance from origin will always be 1, right, and the point at which both of them are intersecting or they are cutting, right, the polar plot and the circle, that point, the distance from the origin of that point will be 1. Okay, that's why that is the gain crossover frequency. What is the definition of gain crossover frequency? The definition of gain crossover frequency is the point at which my magnitude of mobility is 1 itself, right? So I got my omega g, I got my omega p, and from omega g and omega p I can simply calculate the phase margin and gain margin, just as I told you, right, graphically how to find it, right, just here, right, just here. Okay, just here. So yeah, this is basically it for omega g and omega p. Now there are few key points I want to tell you about the gain margin and the phase margin. What is the thought process basically about gain margin and phase margin? If I take this omega g point and omega p point, right, all those points to minus 1,0, then I will get a phase crossover frequency. Okay, I will get my system as marginally unstable, and after that what will happen, my system, like the poles will shift either from left hand side to the right hand side, right? So obviously, due to which my system will become marginally stable, right? Due to which my system will become marginally stable. Okay, so yeah, if I get that critical point, right, my system will become marginally stable. There is a phase crossover frequency in root locus. If there is a phase crossover frequency, then definitely I will, like, it will cross from left hand side to the roots, closed loop roots, poles will cross from left hand side to right hand side due to variation of my gain parameter key. Here also, due to some variation, it may shift to the right hand side, the system may become unstable. Okay, or yeah, that is basically due to variation of OLTF. Basically from there we will understand how does my variation of OLTF translate to my stability for my CLTF. We understood that from root locus, right? Root locus. So yeah, I'm not going exactly back to there, but I hope you're getting your point, right? I hope you're revising also. So yeah, my system will become marginally stable, and after that system will become unstable due to some variation, right? And GM and PM are designed for closed loop system using the frequency response of open loop system. Okay, so like if it is never cutting the, if there isn't any phase crossover frequency, for definitely I can say that there isn't any phase crossover frequency, so hence my poles will always lie on the left hand side, even though how much variation is there, right? How much variation is there, it will never cross to the right hand side. Even if there is slight variation in the poles, right? Slight variation in the open loop poles, or like OLTF, or slight variation in the gain itself, right? OLTF gain, even then, right, my closed loop poles will not shift to the right hand side. They will still remain on the left hand side of my spline. They will still be stable, right? They will still be stable. Okay, even though there is some variation in the gain, right, of the OLTF, they will still be stable, as I don't have any phase crossover frequency. Okay, I don't have any phase crossover frequency. So I hope you got that point clear, right, in your head. So GM and PM are defined for the closed loop system. So they are defined for obviously a closed loop system. They are not defined for open loop system, right? So for open loop system, what is the case? There isn't any case, right? Like we can directly, for open loop system, the open loop OLTF transfer function is the transfer function of the system itself. No need of CLTF, right? So GM and PM are defined for the closed loop systems using the frequency response of open loop systems. So GM and PM are defined for the closed loop systems using the frequency response of open loop systems, basically. Okay, so yeah, like using the frequency system open loop system, we can define like GM and PM, like we can find out GM and PM using closed loop system, open loop system frequency response, but that is defined for closed loop system. If I don't have a closed loop system, then calculating this is useless. So yes, do get this point in your head, right? And like, what is the next point? Now next point is how to calculate my GM and PM efficiently, right? How to calculate that? So what you do, you just make a table, right? You just make a table. Okay, so let me, okay, I don't have a table here, so how to, like, or you can say how to calculate the omega G and omega P efficiently, right? After that, obviously, if you get omega G, you can calculate PM. If you get omega P, you will calculate GM, right? So how to, like, obviously they won't give you graph, and you can will always find with graph, right? Graph is not that efficient manner. Obviously you have to think about it analytically and with equations. How to calculate, that efficiently, right? So for efficiently, what you do, so basically, right, you like make a table, and what are the critical points? Omega equals to 0 and omega equals to infinity. Okay, that those are the main critical points, right? So just as we plotted the polar plot, like you do it like that only. So I will have two parameters, one is the gain and another one is the angle, right? So this is g of g omega into h of g omega, another one is angle of g omega into okay, so this is, and this is omega, right? And this is 0, and let's say this is infinity. So I'm going from 0 to infinity. Okay, so like let's say, like, this is just an example, right? This is just an example. Let's say my gain goes from 10, like it will always reduce, right? Because I will have, my poles will be more than number of zeros. So let's say it go from 10 to 0.1, and let's say hypothetically it goes from plus 90 to minus 90. Okay, so yeah, can we say here that my gain crossover frequency exists? So I can see that from 0 to infinity, as my omega is varying, I'm at some point in between, I'm crossing the what do you say, one magnitude, right? Crossing the one magnitude. So like, what you have to notice is that, like, my magnitude and the phase function, right, they will be monotonic functions. What do I mean by monotonic functions? Monotonic means they will be either always increasing or always decreasing in nature, right? Always decreasing or always increasing in nature. So like phase, right, it will be generally, like, overall, right, overall it will always be decreasing in sense, like overall you can say, like at the end stage it will always be decreasing, because pole will dominate at the end, right? Hence, and for magnitude also, like the it will always be monotonic, right? It will always keep on reducing. So this is in general. It may not happen because if there are zeros present, right, then obviously at starting, like that zero will contribute a positive angle and there will be issues, right? So in general, towards the end, right, towards the end, my OLTF is in general a monotonic function. Okay, monotonic function. Okay, so here, like what I can see is obviously it will cross the 1 point, right? One point. So I can say my magnitude function will. So this is just a shortcut method to find it out quickly. Obviously, when you use the full method, right, then you will understand. So I will tell you that also. So we'll cross 1, right? Hence omega g exists. Omega g exists. And what about this one? This one, right? I can here, right? It is not crossing -180 as I can see, right, in between. But it may exist, right? It may exist. How? When we will solve examples, there will understand it. It may exist. So can't comment about omega p. Okay, can't comment about omega p. That is the only thing that I can say, right? Can't comment about I can definitely comment about this omega g, right? Because definitely somewhere in between, this is a continuous function. As this is a continuous function, it will cross the 1, right? It will cross the 1. This is a continuous function, right? So yeah, as this is a continuous function. Okay, so yeah, this is the basically the few things that you need to keep in mind. Okay, so like here, from here I can easily find the omega g and omega p. So now, right, let's not waste any more time. Let's solve few questions, right? So we have to check whether the gain crossover frequency and the phase crossover frequency will exist or not for the following OLTF, right? For the following OLTF, we have to check whether they will exist or not. How to check, basically? So what you will do, you will simply do the find the angles for omega equals to 0 and infinity. So again, right, what is my, let's do it for the first question. What is my, like, I'm doing the frequency response, right? So I will put s equals to j omega, g of j omega into h of j omega, right? So it is simply equals to 20 by 20 by j omega plus 2. Okay, so yeah, this is this one. Okay, this is not 1 actually, this is 13, right? This is certain, right? So this is certain, then what will happen? Now what is my magnitude function, basically? So my magnitude function is something like this. Let me take another color. Plus 4, right? Omega square plus 4. And what is my angle function? Like we have done this hundreds of time, right? Hundreds of time. This is simply -90. I will not explain it now. Tan inverse 2, right? This tan inverse 2. So like let me draw the table here, right? write the table. Okay, okay. So basically, like, okay, did I do the magnitude here? Like, okay, I didn't to complete the bar here, right? So basically, right, basically, uh, like, what is the magnitude at omega goes to 0? This is infinity, right? Infinity. So this is infinity. And what is the angle at omega goes 0? Okay, this is not 2, sorry. This is omega by 2. Really sorry. Okay, it is, sorry, it is minus 90, right? Minus 90. And what about, like, at omega goes to infinity? So this goes to 0, right? This goes to 0. Magnitude goes to 0. And what about my omega goes to infinity? The phase angle. Phase angle is, this is contributing another 90. So minus 90 minus 90, which is minus 180. So what can I say from here? What can I say from here, right? So definitely I can say that omega gc will exist, right? Omega gc will exist. Okay, also find if they exist. So I should write here also find them if they exist. Okay, so like here for sure what I can say is that my omega g will exist. Omega g will exist, right? And from here itself, the table itself, I can say that this is my omega p, right? So this point, right, this point is my omega p. So omega p is infinity, because like I'm getting phase minus 180 at omega equals to infinity. So that is what my definition of my phase crossover frequency is. The phase, like the frequency at which my phase is minus 180 degree, or at which I'm cutting the negative real axis. So this is what my omega p is, right? So omega p I know, omega g I know will exist, but I have to find it out. So how to find it out? So simply just do the definition, right? So we have already done this, like we've done this example. So what I will do, I will make this magnitude equals to 1. Magnitude equals to 1, right? At what frequency? When my omega equals to omega gc. When my omega is equals to omega gc. So my, like, now simply do it, follow the same procedure, right? So basically my 20 divided by omega plus 4 should be equals to 1. Again I will do the whole square, right? Whole square I will do. So this will be omega square into omega square plus 4 equals to 20 itself. So again, right, I will replace like this omega square to make it a second order equation. Okay, and then solve it. Obviously solving a quadratic equation will be, fourth order equation will be very difficult, right? So I will make my x equals to omega square and make it converted to a second order equation. So x square plus 4x minus 20 equals to 0. So my x equals to minus 4, right, plus minus b square minus 4ac, right, plus minus b square minus 4ac, which is simply 80. Okay, so this is 96 divided by 2a, right? So this is 16 times 6, right? 16 times 6. So okay, did I, okay, one thing again, right, this happens. So I'm squaring this whole equation, right? So what will happen, this 20 will also get square, right? So this is silly mistakes happened with me many times, right? So just be careful about that, right? Don't just blindly go ahead. Okay, so if you're squaring this, right, what we're doing, we're squaring both sides, right? So if you're squaring this, 20 will also get squared. This generally happens in exam halls also, so just be careful of this mistake, right? This is 400, this is also 400. Okay, and what is this? 4 AC, so this will be 1600, right? 1600. I just saw it in the copy, like I did it in rough, right, in copy. Then I just remembered, yes, this is wrong. So if you solve this one, right, you will get two solutions for x, right? One is basically something like this one. So this will be -4 itself, right? And this under root of 16, right, it will be something like plus minus 40.2 divided by 2. Okay, 40.2 divided by 2. So like you will get two solutions of x. I've already written them down, right? So one solution will be 18.1 basically, okay, and another will be negative solution. Okay, negative solution. So basically if you add this one up, so this will be minus 44.2, which is minus 22.1. okay, so you will get these two solutions, right? These two solutions you will get. Okay, but which one should you take? Basically, which one should you take? Basically, right, you will ignore this one. Why? Because what is omega, like what is x? X is a positive quantity, it is omega square, or omega is a real number, right? So omega is a real number. I've already explained this in previous lecture also. Omega real, hence x will be greater than 0. So I will take this one and ignore that one, right? So my omega g square, basically this is omega g, right? Omega g basically, okay, this is actually omega g, sorry, forgot to write this. These are omega g, right? This is omega g. So these are omega g, right? So my omega g will be simply under root x. Okay, under root x. So I've already written it down. What is the value of omega g, right? Omega g is basically around 4.25 radian per second, right? Around 4.25 radian per second, right? So like this is my answer for omega g, and my omega p is infinity, right? Omega p is infinity. Now let's solve the other question, right? So like that's how you find the gain crossover frequency. How to find the phase margin, we'll understand, right? So simply just put the value of angle at that point and we'll do questions on that also. So okay, let me copy this same thing again. Okay, and this time things will be a bit different. Okay, for the 14th question basically, right? For the 14th question. So for what is for the 14th question? For the 14th question, it is 20 by s into s plus 1 into s plus 1, right? Twenty by s into s plus 1 into s plus 4, right? So it is 20 by s plus 1 into s plus 1, right? And like this is omega. Omega square plus 16, right? Okay, so this is this one, right? This is this one. And like what is the angle? Okay, I'm doing it directly now. What is the angle? Angle is like 10 inverse omega by 1. Another like 10 inverse term will be there, right? So it will be tan inverse omega by 4 basically, right? Tan inverse omega by 4, right? So this is the another term, right? So this is another term. Now let's write the values, right, of angle and magnitude basically. Let's see. So again, right, this is simple only. Magnitude condition is simple only. If I put omega goes to 0, so it is infinity, right? It is infinity. And if I put magnitude like omega tending to infinity, this will go to 0. So obviously I will have a gain crossover frequency, right? Obviously I will have a gain crossover frequency. So from here I can definitely say gain crossover frequency will exist. Now what about my phase? What about my phase, right? So phase, right? Phase is basically like omega 0, this is going to 0, so I am only getting minus 90. Now omega infinity, this is contributing 90, this is contributing another 90, right? Hence at total how much I'm getting minus 270. So here, right, also now I can say omega g also will exist. Okay, so let me take another. So omega p will also exist, sure shot, right? How? Because somewhere in between these 2 points, right, I will have minus 180. So I can say it for sure, omega p will also exist. Okay, slowly as you do more examples, slowly we will understand what do I mean by this, what do I mean by this. Slowly, that when that example comes, we'll understand, right? For now, you just understand that if like my critical point is lying between these points, right, then definitely that frequency will exist. Basically, if it is lying like 1 is lying between infinity and 0, definitely my omega g will exist for sure. And if my angle is minus 180, right, like critical angle is minus 180, and here, right, it is lying between this minus 90 and 270, slowly it is reducing, right? Hence definitely my minus 180 will exist between these 2 points, that is for sure. Okay, upper and lower limits are in that range, right? Hence definitely my minus 180 will exist, hence my omega p will also exist. So what we need to do, we need to find the gain crossover frequency, which will be very difficult. Okay, why? Let's see why it will be very difficult and why they won't give you this question to find the gain crossover frequency. Okay, what is magnitude? Magnitude is this one, right? So let me copy this one. So like what is the condition again, right? Let me copy this one again. The condition is basically this, right, should be equals to 1. So this should be equals to 1. So basically, right, this is my magnitude, so which should be equals to 1. Okay, at omega equals to omega g. Okay, at omega equals to omega g, this should be equals to 1. So now what should I do is I need to make it whole square, right? I have to make it whole square. So this should be 400 omega square plus 1 omega square plus 16, right, which is equals to 1 itself, right? Now what is the difficulty? So again, right, if you do like you do the same thing, right? This is omega g, actually, sorry, this will be omega g, so omega g, and if you do like put x equals to omega g square, right, then what will happen, like this will be x into x plus 1 into x plus 16, right, equals to 400. Okay, now what you do, this is x into x square plus 17x plus 16 equals to 400. So this is x cube plus 17x square plus 16x minus 400 equals 0. Now can we solve KV equation just like that without the help of calculator? Okay, like obviously we can solve with using the test points, right? Minus 1 plus 1 plus 2 minus 2, that would do, but that is not a proper method, right? So it is difficult to solve. Okay, so that's why they will 99% chance will not give you this in exam. Okay, to find the gain crossover frequency for order 3 systems, right? Order 3 systems, very difficult to find, right? So for order 3 systems, right? So now like what, like let's say hypothetically we got the solutions of the order 3 systems. Hypothetically we got the solutions. What you will do is, like, you will get 3 solutions, and generally what will happen is either the 3 solutions out 2 will be invalid. How? Either, so we'll write it, out of three solutions, right, two will be invalid. Okay, by invalid what do you mean? Either they will be negative or they will be complex conjugate, or imaginary also you can say, complex conjugate, right? Okay, they will be complex conjugate pairs, right? So like I've already found it out. If you put x equal to 2 here, right, with hit and trial method, if you put x equal to 4 here with hit and trial method, you will get like the solution for this one, right? So like for the solution, other two roots will be invalid, right, and the actual solution will be x equals to 4. Okay, x equals to 4. So what is my omega g? My omega g will be simply 2, right? Just simply do the under root of x, radian per second. Okay, so this is what my omega g is. Now this one was for the calculation of omega g, right here. This part was calculation of omega g. Calculation of omega g. So okay, this is the question, like this part is also for calculation of omega g here, right? Okay, now let's do the calculation of omega p basically. So this is already we have done, right? So still like I'm doing it, like calculation of omega g and omega p we have already done. So again, right, let me copy this one. Okay, just to prove it, yeah, omega p will definitely exist, right? Omega p will definitely exist. So what is my angle? Angle is this one, right? Okay, so if my angle is this one, okay, I need to cut it and paste it over here. If my angle is this one, right, so basically I need to get minus 180 degree, right, at like for calculation of omega p, my angle of h of g omega, h of g omega will be at omega equals to omega p should be equals to minus 180 degrees, right? Minus 180 degrees. So let me copy this one, right? Which is equals to minus 180 degrees itself, right? Okay, so yeah, this one is this one. So basically I can rewrite this equation, tan inverse omega p plus tan inverse omega p by 4 equals to 90, right? Now did I give you some short trick, right? Did I give you some short trick? So whenever the addition of two tan inverse, right, is equals to 90, what is the case? The case is when, let's say this is x and this is 1 by x, then only this will be equals to 90. So omega p should be equals to 1 by omega p by 4. So like this is a short trick, or you can simply solve it using the long method. That also we'll do. So let's first solve it using the long method. So how to solve it? Let's say tan inverse a, I have tan inverse a and plus tan inverse b. So what is the equivalent angle of this one? So it is tan inverse E plus B divided by tan inverse 1 by 1 minus AB. Okay, 1 minus AB. So when, like, if this has to be equals to 90 degrees, when is it possible? Basically, right, basically this has to go to infinity, right? Tan inverse infinity is 90 degrees, so only numerator cannot go to infinity because these are finite. Only denominator can go to 0. This goes to 0, this can go to infinity, so this has to be equals to 0, right? So 1 minus AB has to be equals to 0, so A equals to 1 by B. So from here you can understand that 1 over x and x formula we get, right? 1 over x and x formula we get. So basically A equals to 1 over B, so hence my omega P should be equals to 1 over omega P by 4, right? Okay, so from here we can simply find the omega P value. Obviously we'll ignore the negative solution. Omega P square equals to 4 itself, so omega P equals to 2, right? So the omega P and the omega G both are same. What does that mean? That is very really interesting, right? So if both of them are same, right, obviously my system will be for sure unstable, because it is at both of those points touching the critical angle. We'll obviously ignore the negative what do you say, negative frequency, right? Here if you take the under root of this one, I'll get plus minus 2, right? Plus minus 2, so I'll ignore the negative solution basically. So like if you take the under root of both of these, right, so obviously omega P will be equals to that 2 only, right? 2 only. So under root function will only gives positive values, right? Positive value. So yeah, because omega P equals to minus 2 also satisfies this equation, but obviously I will not use that equation, or I will not use that equation. Basically what I am telling is here, right, what I can do, I can take this 4 on this side, right? Minus 4 equals to 0. Okay, further I can simplify this one. Let me take this one here. Further, this is omega P minus 2, because I will have two roots, right? Second order system, I will have two roots. Second order like polynomial, I will have two roots, so plus 2, right? This is the total expression for this one. So here I will get two solutions. Omega P equals to 2 and minus 2. Obviously I will ignore this one because this is not possible. I will take this one, right? I will take this one. Okay, I will take this one. So, or what you can do is you can memorize few things. How to memorize few things? Basically, right? Basically, like this is the second method that we used to solve it. Like there is some other method also that I solved it in previous question, right? So basically, what you can do is memorize that if I have some transfer function like this one, let's say my g of s into h of s equals to 1 by s into s plus a into s plus b. Okay, then what you can do is you can simply memorize, right? How to memorize? So like don't need to memorize this one, just for the people who are very good at memorizing. So basically what will be my phase crossover frequency, omega p basically, it will simply equals to under root ab. Okay, so you can memorize this formula, you can put it in your short notes, right? Okay, so if my OLT is in the form like this one, my omega p will always be this, right? Under root ab, right? Okay, so yeah, that is one thing. And like this one was the calculation of like this angle using method 1, right? Bit difficult this is using method 1. Now what is another method? Another method is making the imaginary component 0, right? As we solved it earlier also. So method 2, because my angle is minus 180 degrees, okay, it is lying on the negative real axis, hence the imaginary component of this one will always be 0, right? What I'm saying is like the imaginary component of g of j omega h of j omega at omega equals to omega p, right? will be equals to 0 itself, because it is lying on the negative real axis. It is lying at this point, okay, lying somewhere. I don't know the exact gain, right? Don't know the magnitude, but it is lying on somewhere on this axis. Obviously in this axis, if it is lying, then imaginary component is 0. Okay, imaginary component is 0. Okay, so this is this one, right? So hence, how to do that basically. What is my g of s into h of s? It is 20 by s into s plus 1 into s plus 4, and like again, right, frequency response equals to g omega plus 1 plus 2, right? Now what you do is multiply, right? You multiply, or you would have multiplied the s square also, that is fine, but you simply multiply. What do I get? So this is g omega. So this is very hectic. What I will do is, okay, I will not do this right now. Okay, take this one in bottom. So further simplify this one, right? So further simplifying, I will get the same characteristics equation, which is this will be s square plus 5s plus 4 plus 4s, right? So now if I put s equals to g omega, what do I get? This becomes like g omega, like g omega s equals to g omega p. Basically I will put, not now, okay, just simply g omega whole cube plus 5 times g omega whole square plus 4 times g omega basically, right? So now add, okay, let me further simplify it. This becomes minus of omega cube, minus of g omega cube, because I hope you know, right? And this becomes minus of, because I hope we know, because like this, right? If you cube like j, right, you get minus j. J times j is minus 1, again multiply j, we get minus j. So this is minus 5 omega square, and this is 4 like g omega itself, right? Not an issue. So yeah, this is one. So now what do I know? My imaginary of this one will be 0, right? Imaginary of this one will be 0, that we know, right? So if my imaginary of this one will be 0, what does that mean? That means that like this imaginary will be 0, right? I can say this imaginary will be 0. If this imaginary is 0, obviously numerator is real itself, so the imaginary component will be 0 itself. So I can find my omega p, right? Imaginary part of this one is 0, okay, at omega equals to omega p, right? So yeah, so this is, so what does this mean? What is the imaginary component of this one? The imaginary component of this one is minus omega cube and plus 4 omega equals to 0, right? So from here I can say that omega equals to 0 is not a solution, obviously, because at omega 0 I know my phase. My phase is, okay, I have to go to my omega equals to 0, my phase is minus 90, so it is definitely not a solution. So omega into omega plus 2 into omega minus 2 equals to 0. This is omega p, right? So basically I'm getting 3 solutions here, right? And I will ignore 2 solutions. So basically omega, like this is omega p itself, this is omega p itself, this is omega p itself. omega p basically can't be equals to 0, as at that my angle is angle of j omega and h of j omega, right, is minus 90. So that is not possible, right? So this is not a solution. Okay, we'll just cut this one. This is not a solution, right? Now what about my, like, I already know, we have already covered this, right? Omega p like will be equals to 2, and omega p can't be equals to, omega p can't be negative, right? So like we have already established this one, and this one will be the correct, and this one will be my answer, omega p, right? So yeah, so like let me take another page. Hence, what is the significance of this omega g equals to 2 radians per second, right? And omega p equals to 2 radian per second. Do let me know. But my omega p and omega g both are at same frequency, basically 2 radian per second, right? Now like this I've already told you, right? All these things I've already told you. So I'm giving you a few homeworks, right? Already lecture has gone pretty long. So what are the homeworks? The homeworks are these two things. Basically find the relative stability parameters, basically the gm, pm, omega g and omega p, all these things, right? You have to find. Okay, so for all these 4 voltage, take the screenshot and find the relative stability parameters. I will summarize in the next lecture what happened in this lecture, right? Yeah, thank you for watching.